CBE 360, this is an expert from Marlin's textbook, Process Controls and Dynamics. Chapter 2, Control Objectives and Benefits. The introduction. The first chapter provided an overview of process control in which the close association between process control and plant operation was noted. As a consequence, control objectives are closely tied to process goals, and control benefits are closely tied to attaining these goals. In this chapter, the control objectives and benefits are discussed thoroughly, and several process examples are presented. The control objectives provide the basis for all technology and design methods presented in subsequent chapters of the book. And this chapter is titled Control Objectives, so in this chapter we will be learning about the control objectives and possibly the design methods. Oh, actually, the design methods might be referring to process design schematics, and those are presented in the later chapters. So right here, we are talking about the control objectives. And this might even encompass the figure 2.1, even though the objectives, I'm not sure if that's synonymous with elements. While this book emphasizes the contribution made by automatic control, control is only one of the many factors that must be considered in improving process performance. Three of the most important factors are shown in figure 2.1. And figure 2.1 indicates that proper equipment design, operating conditions, and process control should all be achieved simultaneously to attain safe and profitable plant operation. Clearly, equipment should be designed to provide good dynamic responses in addition to high steady-state profit and efficiency, as covered in process design courses and books. Also, the plant operating conditions, as well as achieving steady-state plant objectives. The operating conditions should provide flexibility for dynamic operation. Thus, achieving excellence in plant operation requires considering all factors, and this book addresses all three factors. It gives guidance on how to design processes and select operating conditions, favoring good dynamic performance, and it presents automatic methods to adjust the manipulated variable. Most of the text in the second paragraph is really just fluff. The main things in this paragraph are the factors, and we saw that control is one of the many factors, but there's three important factors. So the three important factors are the design equipment, the operating conditions, and the process control. So I believe control and process control is synonymous, or leads to the indication of a same conclusion. A little bit spaced out in our wording. Move on to section 2, control objectives. And on the second page, we can see the control objectives, 1, 2, 3, 4, 5, 6, 7. Here we can double check just before we start the paragraph and before we start the section, we can double check if the control objectives are the same as the elements / factors. So that important factor in figure 2.1, let's check it out. So we have the equipment design. It doesn't seem like we have that in here. We have the operating conditions, smooth operation, then we have process control. And honestly, those three important factors can encapsulate the control objectives. When you think about process control, you have to think about the safety, the environmental protection, the equipment protection. You have to think about all of this. And that might be partly why the chapter is titled Control Objectives, when, the process control encapsulates these control objectives, but when you think about the operating conditions, you also think about all of the control objectives, and when you think of the equipment design, you also think about the control objectives. So the process control, the operating conditions, and the equipment design really encapsulates the same words. When you think about equipment design, process control, and operating conditions, it might be, when you think about those three things, you think about all of the control objectives, you think about the parameters, and all of those parameters are encapsulated under the control objectives. Now, it might be finicky saying parameters because parameters sometimes indicates a value, but in the same sense, these control objectives are of value. So this is just some little mixing up in your head that you can correlate these things together, the process control, the operating conditions, the equipment design, they all encapsulate and incorporate the control objectives. And even the figure is a schematic for achieving plant performance. Kind of just trying to tie them all together. I don't think this is really important, but we can go ahead and edit this. We can go ahead and finish the entirety of the chapter and edit the chapter and upload it to my YouTube channel. I gotta finish my sentences sometimes. The 7 major categories of control objectives were introduced in chapter 1, and they are discussed in detail here, with an explanation of how each influences the control design for the example process shown in figure 2.2. Figure 2.2 is shown on the next page. The process separates two components based on their different vapor pressures. The liquid feed stream consisting of component A and B is heated by 2 heat exchangers in series. Is heated by 2 exchangers. So I think it's okay to say heated by 2 heat exchangers. And it's kind of imperative to show the figure 2.2 while I'm reading this paragraph. So the first paragraph of the second section is talking about figure 2.2. It's incredibly stupid to have a figure on the other fucking page. So dumb. So the stream flows through a valve to a vessel at a lower pressure, and as a result of the higher temperature and lower pressure, the material forms 2 phases. So higher temperature and lower pressure. Higher temperature is speeding up the movement, and the lower pressure is allowing that movement to flow relatively easily. And actually, relatively might not be the best word here. As you lower the pressure, it's easier to form another phase. And that goes back and ties to the temperature and pressure graph. It's just a fact. And when you think about it, when the temperature increases, you have the phase equilibrium graph. That's what I'm trying to get at. You don't have a temperature and pressure graph. You have the phase equilibrium graph. So you have the solid, gas, and liquid phases. So increasing the temperature along the graph of a phase equilibrium graph Increasing the temperature would make you go up, so temperature is on the y-axis. Increasing the temperature, you would go to a gas. So a gas is on the very top, a liquid is in the middle, and a solid is at the bottom. But I'm also unsure if where that gas is on the graph, because a typical phase equilibrium graph is, it's very easy to remember. So here it is. I just made these lines to show the cutoff point of the line just because I drew it a little bit too big. But here's the phase equilibrium graph, and I'm assuming that the temperature is on the y-axis and the pressure is on this side. So increasing the temperature would make you go up. And I believe this is the gas. I believe this is the solid. But that doesn't make sense if temperature is on this axis. So increasing the temperature would make you go to a gas. And if you have a high pressure and a low temperature, you would be at a solid most likely. High pressures. But as you increase the temperature and you stay at the same pressure, you could go to the liquid phase. And if you increase that temperature even more, you could go right here. But if you decrease the pressure, so if you decrease the pressure at the same temperature, so the temperature is on the x-axis, decreasing the pressure would make you go from a solid to a liquid. And this is not common. This is called sublimation right here. So more times you're around here, more times you're around here, more times you're around here. At least that's how we've been presented the information, just to talk about it a little bit faster. Let's go back to reading the book. So as a result of the high temperature and low pressure, the material forms two phases, with most of the A in the vapor and most of the B in the liquid. The exact compositions can be determined from an equilibrium flask calculation, which simultaneously solves the material, energy, and equilibrium expressions. Both streams leave the vessel for further processing, the vapor stream through the overhead line, and the liquid stream from the bottom of the vessel. That makes sense. Overhead line. You don't even need to know these adjectives like overhead line. The vapor just leaves from the top of the chamber. You don't have to learn all this new lingo unless it's being presented when you're at your job. If they're really wanting to say the overhead line, they'll make emphasis of it. I don't think there's that much emphasis on this overhead line. And I don't even think this is important text. I think this is just fluffing. Although a simple process, the heat exchanger with flash drum provides examples of all control objectives. And this process is analyzed qualitatively with control in chapter 24. So this is a simple process they're talking about. Figure 2.2 that does not look simple to me. And it's as if the author, Mr. Moreland, is belittling the reader by saying this is a simple process, because further in the textbook, or just further down the line when you're doing the course, and even just for this chapter, like the next upcoming quiz that would be expected of you, you would not have to draw this entire figure that there is 2, 4, 6, 8, 10, 12 controllers. Excuse me, there are 12 instruments. There's indicators, and there's controllers, and there's even valves, there's a flash drum, there's a centrifugal pump, and there's a safety valve. And when you think about it like that, that is really simple. When you think about it, like I would write this initially, but sometimes the professor dumbs down the schematics so much that you can't really remember what you read about. Like, this is so simple in my head. Like, of course, there's going to be an inlet stream, and if you have a heat exchanger, you're just going to have water flowing through that pipe, because the pipe goes into a heat exchanger. It just makes sense. Continuing on, a control strategy is shown in figure 2.2. Since we have not yet studied the calculations used by feedback controllers, you should interpret the controller as linkage between a measurement and a valve. Thus, you can think of the feedback pressure control system, PC, as a system that measures the pressure and maintains the pressure close to its desired value by adjusting the opening of the valve in the overhead vapor pipe. The type of control calculation will be covered in depth in later chapters. It's not critical for the discussion of this chapter concerning the control objectives. Moving on to safety, the first control objectives, and we will be talking about the 7 control objectives in chronological order. The safety of people in the plant and in the surrounding community is of paramount importance. While no human activity is without risk, the typical goal is that working in an industrial plant should involve much less risk than any other activity in a person's life. What? That doesn't make any sense. The safety of people in the plant and the surrounding community is of paramount importance. While no human activity is without risk, the typical goal is that working in an industrial plant should involve much less risk than any other activity in the person's life. So they're saying driving a car is more riskful than working in a chemical plant. Okay? They're not saying that it is. They're saying that's the objective. And I think that's not a feasible objective. But honestly, when you do think about it, I don't think I hear any news about nuclear power plants or chemical plants or factories being exploded or any accidents. At least I don't even have a news feed for that, So just a note, no compromise with sound equipment and control safety practices is acceptable. Plants are designed to operate safely at expected temperatures and pressures. However, important operation can lead to equipment failure and release of potentially hazardous materials. Therefore, the process control strategies contribute to the overall plant safety by maintaining key variables near their desired values. Since these control strategies are important, they are automated to ensure rapid and complete implementation. In figure 2.2, the equipment could operate at high pressures under normal conditions. If the pressure were allowed to increase too far beyond the normal valve, the vessel might burst, resulting in injury or death. Therefore, the control safety strategy includes a controller labeled Pressure Controller 1 that controls the pressure by adjusting the valve position, or the percent opening, in the vapor line. Figure 2.2, we have a pressure controller right before the safety valve. And notice that if the safety valve is closed, regardless if the pipe is lower than the safety valve, that air will just be trapped up in the exceeding length of the pipe, above the exiting pipe. for the vapor, just because it's in the safety valve, just below the safety valve opening. But you also have to account if there's a pressure if there's a pressure gradient and the pressure and flow, if the pressure is causing the flow to leave through the exiting pipe, that liquid that is just before the inlet of the safety valve would be caused to move out just because the flow is existing. And, materials like to move together. That's really due to pressure gradients. Another consideration in plant safety is the proper response to major accidents, such as equipment failures and excursions of variables outside of their acceptable bounds. Feedback strategies cannot guarantee safe operation. A very large disturbance could lead to an unsafe condition. Therefore, an additional layer of control termed an emergency system is applied to enforce bounds on key variables. Typically, this layer involves either safely diverting the flow of material or shutting down the process when unacceptable conditions occur. The control strategies are usually not complicated. For example, an emergency control might stop the feed to a vessel when the liquid level is nearly overflowing. And proper design of these emergency systems is based on a structured analysis of hazards that relies heavily on experience about expected incidents and on the reliability of process and control equipment. In Figure 2.2, the pressure is controlled by the element labeled PC. Normally, it maintains the pressure at or near its desired value. However, the control strategy relies on proper operation of equipment like the pressure sensor, and the control strategy could be improperly. Let me say that again. However, the control strategy relies on the proper operation of equipment like the pressure sensor and the valve. Suppose that the sensor stops providing a reliable measurement. The control strategy should improperly close the overhead valve. Okay, so suppose that the sensor stopped working, providing a reliable measurement. The control strategy could improperly close the overhead valve, leading to an unsafe pressure. I don't think the overhead valve is talking about the safety valve. I think it's talking about the exiting vapor streams valve. So if the pressure controller, I don't know why we don't have a pressure indicator and a pressure controller. I think we ended up saying if it's like a dark circle that also indicates a indicator. But that wouldn't make sense because we have dark circles and blatantly labeled TI in a dark circle. So I'm not sure. I think the dark circle means a controller or an indicator. I'm not entirely sure. But it doesn't make sense that we have a pressure controller and we don't have a pressure indicator. Like that pressure controller would have the indicator encapsulated inside of it. So like, why would I get marked wrong on my quiz just for putting the extra information? Like, fuck you. But this is also something. We have the analyzer controller, and that does composition. And notice that you don't have the analyzer indicator for the composition. I just assume that they're saying it goes through this controller, it creates a reading, and the controller acts accordingly. Maybe that's exactly how they're trying to say it. In Figure 2.2, the pressure is controlled by the element labeled PC. Normally, it maintains the pressure at or near its desired value. However, the control strategy relies on the proper operation of equipment, like the pressure sensor and the valve. And suppose if the sensor stopped working, the control strategy could improperly close the overhead valve, leading to unsafe pressure. The correct control design would include an additional strategy using independent equipment to provide a very high pressure. For example, the safety valve shown in Figure 2.2 is closed unless the pressure rises above a specific maximum. Then it opens to vent the excess vapor. It is normally important to recognize that this safety relief system is called on to act infrequently, perhaps once a year or less often. Therefore, its design should include highly reliable components to ensure that it performs properly when needed. Because sometimes you can get stale, just sitting in the same place forever. Sometimes when you have a PID, a process instrumentation diagram as shown like this, and it's not vividly and descriptively drawn completely, like you might have a closing before. You might have like a small apparatus or just a small flap that closes to not allow gas into the inlet pipe of the safety valve, because you might want to prevent fouling and corrosion. It wouldn't make sense. It wouldn't make sense not to have it, unless there's a cost safety, unless that equipment, it wouldn't make sense unless that equipment is specifically documented and researched to have a sustainable lifetime that is greater than a year. So, moving on to the second control objective, the environmental protection. Protection of the environment is critically important. This objective is mostly a process design issue. That is, the process must have the capacity to convert potentially toxic components to benign materials. Again, control can contribute to the proper operation of these units, resulting in consistently low effluent concentrations. In addition, control systems can divert effluent to containment vessels should any extreme disturbance occur. The stored material could be processed at a later time when normal operation has been restored. In Figure 2.2, the environment is protected by containing the material within the process equipment. Note that the safety release system directs the material for containment and subsequent neutralization, which would involve recycling to the process or combustion to benign compounds. I don't know what benign means, but how about we context clue this bitch? Note that the safety release system directs the material for containment and subsequent neutralization, which could involve recycling to the process or combusting to benign materials. Combusting rings a bell in my head of an oxygen process, but combusting also rings a bell in my head. Combust. And once you do that, you break apart, you have little crumbs of your molecule, so they disperse, and that combustion reaction, I'm pretty sure it encapsulates an explosive oxygen reaction. I would believe benign materials and benign compounds really just mean elemental elements. So elements that would be safe, relatively safer if it didn't undergo the combustion or the neutralization. The neutralization was really the key indicating word for me. Moving on, for example, a release system might divert a gaseous hydrocarbon to a flare for combustion, and it might divert a water-based stream to a holding pond for subsequent purification through biological treatment before release to a water system. Equipment protection. Much of the equipment in a plant is expensive and difficult to replace without costly delays. Therefore, operating conditions must be maintained within the bounds to prevent the equipment damage, and these types of control strategies for equipment protection are similar to those for personal protection or personnel protection. That is, controls to maintain conditions near desired values, and emergency controls to stop operation when the process reaches boundary values. All of this information that I'm reading is boring me. I'm literally having to speak twice the amount that I would be speaking just because it's so boring. It's so simple. In Figure 2.2, the equipment is protected by maintaining the operating conditions. I don't want to read that. Let me read it anyways. In Figure 2.2, the equipment is protected by maintaining the operating conditions within the expected temperatures and pressures. In addition, the pump could be damaged if no liquid were flowing through it. Therefore, the liquid level controller, by ensuring a reservoir of liquid in the bottom of the vessel, protects the pump from damage. Additional equipment protection could be provided by adding an emergency controller that would shut off the pump motor when the level decreased below a specific value. Now we're done with equipment protection. We're going to move on to the third operating condition. And I just want to scroll through the entirety of the chapter to see if there's any other instances of control objectives being explained in more depth. Looks like there's not. Looks like we have 20 pages to read in total, and we're on page 5. It's taking me 30 fucking minutes. God damn. I don't think this is an important chapter. So, for this chapter, look like I'm reading my books. For this chapter, I'm going to finish up section 2.2, and I'll just upload it. Because there's no point in me learning about the equations that are presented in the later sections. Because I remember these equations. I remember I didn't do that good, but I remember that there's no instances of these equations being used in the subsequent chapters. We have the mean, the standard deviation. Those are not what I'm talking about. I'm specifically talking about 2.3's equation. It's the average process performance. I don't know how the fuck I got that wrong. I don't know why I didn't look at examples. There's only 2 examples in the fucking book. I read the book and I see there's no examples pertaining exactly to what I'm doing. Example 2.3, example 2.4, example 2.5 have no algebraic manipulation included inside of it. So what are they expecting me to do? Find the answer manual? I don't know where the fuck the answer manual is. How the fuck am I supposed to find that? And even if I did, the answer manual might only even give me odd answers. It might even only give me odd answers. Let's finish up the rest of the control objectives. Actually, let's not finish it up. I can finish it up at a later time when I really feel like I have free time. But right now, this has no information that I really even want to put into my brain. So right now, I'm going to create all the pictures that I will be uploading to the YouTube video for editing. And I will finish the editing process right here and right now. It's taken me 30 minutes. I've taken out 1/3 chunk of my day. It's taken me 30 minutes. So this is a 1/6 chunk of my CBE 360 work for the day. It will take me maybe another 15 minutes. So maybe an entire hour devoted to this chapter 2. And that's okay with me. Chapter 2, chapter 3, 1 hour, chapter 4, 2 hours. So I really could read through chapter 1. I could read through chapter 3, 4. Okay, so this is already gone. 3 and 4. Maybe I could devote the entire day to CBE 360. I always go down this route of devoting the entire day, and then I don't have any other, like daily quizzes or Quizlets about CBE 360. I just say, okay, I did it in one day. Hopefully I remember it for next time. That's what I do. So these YouTube videos really help me just to say, in my head that, okay, I did the work. I saw that I did the work. I'm watching myself read the fucking textbook. If I just sit here and listen to myself, my previous self, that smart man right there that literally made the video, I'll be good. Because me in the present watching that YouTube video does not have to read the fucking textbook. I just gotta follow along with my lines. I just gotta follow along the words on the lines of the page and just listen to myself. And I really liked my voice today. I thought it was very soothing. We're at 36 minutes. This will be dwindled down to 20 minutes, 20-minute editing process. It will take me 1 hour to complete this entire chapter. It will take me 1 hour to complete 7 pages. It'll take me 1 hour to complete 3 pages. God damn, that's horrible. But that's okay. I'm in the zone right now, so that's good.